manufactured for the first Titan hull. Lieutenant Steele, can you display Exhibit 105? And zoom into the delivery date for the first window. And I'm reading December 6, 2017. So to clarify for the record, the report that we're looking at was created after delivery of the viewport and was done in 2018.
Mr. Newbarber, just to clarify, the report was prepared on the basis of the design drawing of the viewport, not the viewport itself.
That's correct. I understand it was just going off the drawings. The viewport was not delivered to to Kemper Engineering that conducted the analysis. Okay. Okay. Mr. Kemper, do you remember when you started this report and approximately when you finished it?
I started it sometime in December, and the email here on the next page, if you zoom in, is January 30th. So it's towards, it's in the formal report I sent had the original report, had dates on it, but this email went forward January 30. So of the next year of 2018.
Okay, and was this email in conjunction with delivery of the report to
Yes.
OceanGate? Okay, thank you, sir. Are you ready to proceed to this slide?
Yes, I am. Okay. So the results that were indicated here is that I indicated possible cyclic fail and then specified that the Cyclops design, that was a name at the time, it was not called the Titan at the time, at 5,800 PSI, indicates significant strain that is consistent with potential short cycle failure modes. What I was lacking, to be more definitive, was I did not have the head design. The head, I had a window seat that's basically just a mating surface, and it's very rigid, and I use it to analyze the window itself. But to actually predict the window, it's going to act as a part of the pressure vessel boundary. So to be more precise, I would want to have the actual head design so the flexibility of that head would be incorporated in the response. So that was one of the things that Will and I talked about, is basically, look, Will, this looks iffy. I'm not sure. I can't say right now this is going to be one of those ones that fail in 50, 60 cycles, but I have concerns. So that was the basis of this going forward, and I was CC'd on the email. In fact, and they said, "Thanks, Will Bart. I will consider this and discuss this with my team. All the best, Tony Nissen, Director of Engineering, OceanGate Incorporated." So I never heard anything more from them.
Can you explain the data you were the head design data you were seeking?
Well, just the design of the head, or what that I didn't actually have the seat itself. If I know it looks like these metal heads are metal, and I mean they are metal, but they look like they're very stiff. They are, but when you're talking thousands and thousands of pounds of force, of pressure, it's going to deflect. It's going to move, and how that moves could make things better, could make things worse, because it's going to interact. As I said earlier, the reason why acrylic was selected, because it deforms just that little bit to the seat. And using a nonlinear analysis with contact elements allows the seat, the window to move against the seat. And if the window under pressure, the window itself flexes, the viewport as a whole flexes as it adjusts to pressure, the window would, being nonlinear plastic model, would adjust with it. So what I had was just very much just the outside shape being held rigidly to just compare that to my previous work, because that's how I was reviewing Dr. Jerry's work. Was he was using test items, I was replicating the test items that were massively rigid compared to the shapes that he was testing, and I was learning to interpret the stress strain versus the stated results. And in specific, this seemed consistent with the ones that when he tested that given design at the test pressure he used, it had an annotation of failed in 50 cycles. Another one was failed in 16 cycles. So it was not consistent with the ones that failed the first time through, but it failed under a short number of cyclic loadings, which it shouldn't do. So that's when I saw that strain pattern, that's what caused me to be concerned, and write the letter that I did, write the report the way I did. But I could not confirm it without having that data. And also, I was using as a material curve, there is a standard acrylic called Mill Standard P84, and that was used a lot in Jerry's testing. So because Jerry was using that in his testing, I was using that to replicate his work. Modern acrylics are cross-linked. They're stronger and better. So to actually predict the actual window results, I would also use the actual stress strain curve for that window. So when Will approached me, he did not give me details about his clients. He said, I have concerns for, can you please look at this? And I acted accordingly. So I didn't, that's as far as it went at that time. My anticipation was, hey, why, at least ask me the question, why do you feel this, why do you feel this might be a short cycle failure? I anticipate at least a question. There was nothing that came back. Not well, will it leak or will it crack? Or no questions about what the failure mode would be. What should we anticipate? If we use it, what would it look like? So there was no interest in any communication whatsoever. They didn't even ask me, how'd you come up with this, to see if I was modeling this the right way. They didn't have any interest in talking to me about that. So it's, that's as far as that went at that time. I found that a little bit disturbing, but I'm not the only engineer out there. And there are other people doing things. And can I go back and talk about what I spoke with Stockton Rush in 2016? It applies to this.
Can you clarify, was that at the annual meeting?
At Underwater Intervention Marine Technology Society meeting in New Orleans in 2016.
Yes, sir.
Okay. He made it very clear that I may have an aerospace degree, but I'm not the engineer. I'm going to hire an engineer who knows what they're doing. That is the right answer. And that to me, I just met the man. I didn't know him. That to me seemed absolutely reasonable. That great, you have a technical background, but being the engineer is a full-time job, and that's your whole focus. And you don't want the money guy to also be the person being the engineer. Because if I was the money guy at my company, I would have all the toys, and we wouldn't be paying bills. So him saying that I would, I'm going to hire these really good engineers and consult with people. It's like, okay. So my thought was that I informed him. He wasn't sure about it, and he went to his team, and that's what they said. I'm going to go talk to my team about it. So I was not concerned as in, oh my God, I think these people are going off the deep end. I figured they just took their work to their team and went to their people and figured and made a decision based on that. So I had a basis by which to interpret this, that when they said my team, that knowing that he's working on submarines, that he is talking to some of the other people in this field that are doing good work.
Sir, so you did not follow up beyond this email?
No. If I would have felt the need to, I would have. If I would have actually felt more concerned, I might have gone to the Board of Registration or some other, I would have acted in a more decisive manner. But I had every basis to think the Stockton Rush would be acting in a reasonable manner.
Understand. And so I'd like to just ask a question about the 0.26 inch expected distance of on the previous slide. You had estimated I think 0.26 inches of movement
Correct.
of the bottom of the window along the seating surface. Is that correct?
No, I estimated 2.6 inches along the center line. So it would be basically, as you look at the window, at the round window, it'd be the middle. Because it would pooch out, it would pooch out pooch out in a dome. So it would be, be a round dome and be right there in the middle. So that was why I'm saying that's more difficult to track, but the edge of it where it enters, where it's riding the window seat is much easier to measure. And that's why I thought that a layperson, when they said they saw it move 3/4 of an inch up and down the window seat, I was concerned that might be what they're measuring, because that would be more extreme than just what I had.
And just to clarify, it is 0.263 inches.
Yes, 0.263.
Would there be a concern if it was greater than that by a margin of?
By a significant margin, ×3 is significant.
But what would be a possible cause? What does that indicate, in your opinion?
I have slides that address that.
Okay, let's proceed.
Okay. So is everyone good with this slide right now? We can move to the next one. Okay, so what we have next is the conical section, spherical sector window that would sit in the same space as the OceanGate one. So in other words, the top rounded part is still there, and then you're just putting in less acrylic. We're just making this a spherical sector. And the right image was from the SolidWorks models that I developed, where I had the SolidWorks model of the Cyclops window, later became the Titan on top, and bottom was the alternate design using a spherical sector. Now this was developed, this analysis coming up was done post-incident. So this is when I knew that I was going to submit something to the NTSB. I anticipated the questions would be, well, what would happen if you use a spherical window? What about this? What about that? Also, as of 2003, I had 5 more years of working in design by analysis. I had a little bit more refined my techniques. More people had published. I had published more. So I had a little bit more of a refined technique when it came to modeling. I chose not to redo my old work and just present what was done in 2018 as transmitted. So the next one.
Mr. Kemper, just to clarify, the image on the left is not the design of a viewport that was manufactured for OceanGate. The one on the right is that?
The one on the left was not for OceanGate. The top one on the right was for OceanGate. The bottom one on the right is the same as the one on the left.
Okay, thank you.
Not a problem. So slide, please. Okay, this is how simple Jerry Statue's method is. So the critical dimension to do this is going to be the bottom of the window seat, which right there is 15.2 inches. So I need that number. I need to know, and since this is a non-standard window, I selected that this was going to be similar to an acrylic spherical window with a conical edge, because I needed something to use Jerry's method. And due to the depth it was diving to, it has what's called a CF of 4. You look it up for the temperature. It's going to be 50 degrees, CF 4. It's that simple. Now, the CF is correction factor. That is not a design margin. It's not a safety factor. In fact, Kaylee Williams of Lockheed Martin and I presented a paper several years ago where we went through the CFs and tried to figure out, is that an actual design margin, or is there a relationship of CF to design that we could pull as a design margin, so we could basically back out how reliable, what that safety margin is for Jerry's designs. and we could not find a correlation. It works, and some are more conservative than others, but it's not a design margin, and you cannot treat that as a design margin. But you take that, you multiply your design pressure times 4, I get a number, 23,200 PSI or 160 megapascals. Then I find the right graph in the book, and because it's 90-degree angle or 40, a 90-degree included angle on the window seat, I'm using 160 because the other one, that's the other side didn't have the US one. You go to 90 degrees, you drop down, and it gives me a T over DI, which is the thickness over the diameter. That now gives me my thickness. It's that simple. At no point am I putting a single material property in here. I could double and triple the material strength. I could increase the stiffness. The design does not change. This is why we're doing design by analysis, and it's a slog to do this. And if you would have presented this to me as a good idea on its own, I would have a lot of issues. But this has 70 years of proof, and before they even did that, they had 20 years of testing to back that up. So I know this is shockingly simple for such a critical item, but when people say that Jerry Statue was conservative in where he put his design lines, he was, because of the uncertainty, because at that time, with the tools available, there was just not a reliable way to model this directly with mathematics like we would a beam calculation. So that is the PVH01 design method. Now, there is more art and science where you're doing the window seat, the whole mechanism and how it interacts with your rest of your pressure vessel. There's a lot more to it, but the acrylic section, that's it. Any questions? I know all the technical people are going, this can't be that simple, but it is. So let's go to something that's not as simple. Let's go to the next slide. This is showing the Titan window, the Cyclops 2 window, and then the exact same seat and same spherical section and as a spherical sector. They both deflect about the same amount. Axial deflection on the bottom left is 0.204 inches. Again, I'm using a more refined method than I did 5 years prior. With the spherical sector is 0.18. However, look at the strain. On the left-hand side, peak strain is around 16%. It's highly, highly localized. And when you see very localized strain, that is consistent in any material with a potential tear or cracking. I mean, all the energy, all the pain and suffering is going that one small point. And typically, acrylic has a max strain somewhere between 4 and 8%. So this is also showing that you're likely to have exceeded it, and you probably had some gross local deformation, but all that residual strain is in there. Now you look at the spherical sector, peak strain is 0.25%, much lower. It's still pretty much elastic. And the elastic part is not just about the peak strain, it's also about how the rest of the material stays well in the elastic region and forces the whole thing to act as a unit in an elastic manner. So this raised significant questions, which is why I did the next analysis.
Mr. Kemper, before we go to the next one, I just
Sure.
wanted, and for the record, none of this seems simple to me. So the prior slide or this one, but the post-incident analysis, what was that done? I assume the incident is the Titan tragedy. What was the analysis done? What were you using for the analysis?
I still had the same model, the same geometry from previous. So I used the same window design that was presented to me in 2018. And then I used I confirmed Will Conan's spherical sector design. He said that he did it according to PVHO. I backed out and got the same numbers he did. And that was what I did to compare the two, because there's a legitimate question, what would happen one window versus the other in terms of looking at this from a failure analysis or a systems perspective, which is my intention with going to the NTSB. This was not meant to be, and I didn't go to Will with this. This was not about Will's choices, or not about Ocean Gate. This was submitting this to a jurisdictional authority for them to decide whether it's relevant or not. I honestly didn't know if my report would be seen as relevant, but I knew I had to submit it.
Understood. So just to clarify, it's basically additional analysis on the data that you had from 2018. Is that
Correct.
fair? Understood. Thank you.
Not a problem.
Sir, did you have any updated information on the seating surface at this time?
No, I did not. I did not have the designs of the head.
And can I clarify also that on the left-hand graphs, that would be the Titan's design, and then on the right-hand side, that would be just a window that is curved inside?
That is an ASME PVH01 spherical sector. So the point of it is, it's not a question of that Will was looking at this. I did the work to verify this is for that critical dimension and that pressure, that is going to be the ASME design that you get every time.
Thank you.
Now, we've talked about elastic and plastic, and we talked about how plastic by nature stays bent. You bend it and it stays bent. That's the definition of plastic when you're talking about metals. So, as I said, I had some more experience at this point, and there's been more studies put out at this point. So if you can go to the next slide. What I'm going to show here is a loading and unloading, where the curve on the left shows that it's called a pseudo time load. In other words, it's actually not representing any particular time period. It's just saying I increased the load up to the max amount at a certain rate. As you got closer to a certain rate, it curves over and slows down the rate. In the middle of the curve, which would be 0.5 seconds, it's not actually seconds. It's just 1 second is unity, so 0.5 is half that time period, is at peak, and then it comes back down. The reason for this is that when you're looking at nonlinear curves and things stay bent, it's all interacting, because you have the parts that are still very plastic but compressed like a spring, and they're pushing back. And then you have the parts that have been deformed, and then they can be deformed back into a shape. So by loading and unloading, I was able to use this technique to replicate some of the impending failures from Jerry Statue's work. So this one cycle load is not meant to be used for fatigue loading or for something like that, but it is. I did find this to be a much more precise way of looking at a window with respect to failure modes, as verified by comparing it to Jerry Statue's data. And when I say Jerry Statue's data, when he presented his papers, he included his test methods, his uncertainty. He would have large appendices to his actual paper that was published. In the Navy papers, he would have all the extra data available. So I was basically able to go through his lab reports and get his notes on that. So this is showing that it's a refined mesh without going into detail. You want finer mesh where you're having a lot more things going on with the stress and strain. It goes to how large the model is in the computer, but what this is meant to say is that there's a pretty good, this is something that my professors would arguably call overmeshed. But with modern computers, I can overmesh something and let it run and get it faster than back in the old days when we had to do, literally plot every little mesh point by hand and type in the commands. So it wasn't uphill both ways, but it felt like that. So can we go to the next slide, please? Okay. So this is the result of one cycle. Going into 0 point on the way up means nothing because it's not loaded. So I'm comparing 1,000 pounds of pressure, 1,000 PSI, on the way up, and then 1,000 psi on the way down. The top picture is on the way up. The bottom picture is on the way down. The difference of what you're seeing is residual strain. In other words, and also if you look at the top picture, you'll see a little bit of white space. Even at 1,000 pounds, it's still loaded. It's already pulled away from the window seat. That white space is to scale. What this means is that it was pushed down, and that flat part at the bottom was permanently deformed inwards. It's very much like an extrusion die. Now, the top part is elastic because it has all, it's not as directly, you can see, it doesn't show all the strain. So the top part is very elastic. It's not permanently deformed. So as you take the pressure off, it pulls it back up because you have it pressed down, it's acting like a spring. You take the pressure off, it's pushing itself back up, just like it would in real life. What's significant about that is that every time you cycled this will happen again. In other words, every time with this particular design, every time you cycle with that high localized strain, it's going to push it again and push it again and push it again. Now, what's going to happen over time, a number of cycles, is the top of the window is going to be in full contact with the window seat because it's elastic. It's going to be right back where it started. Sorry. It'll be right back where it started, but the inside, on the low pressure side, is going to have a gap. And it's going to be watertight because the top side is the water side. But now when you press on it, there's going to be a period, a space where there's only a little bit of contact at the top, and it's going to scoot down quickly until it picks up the rest of the material, until it picks up the corner, and basically. Because if you now have taken it and pulled the angles in a little bit, only the parts that are in contact are providing resistance, and it comes in more. So when I did this analysis, again, I was trying to get a better handle on this design, and the open source news, which is not engineering data, said it came in 3/4 of an inch. This behavior is consistent with the model, that over time, it would have deflected in such a way that as it pressurizes, it would scoot in rather quickly until it picks up the last point that it was fully engaged, and then fully engage and take up the load again. This is an example of why the ASME designs, whatever Jerry did, how much testing he did paid off because those conservative curves kept us away from this behavior. But this behavior here is consistent with potential failure.
Sir, I want to follow up on that. So does that mean, in your opinion, that this design is problematic with a flat surface?
Absolutely, yes. Now, I want to caveat this. This has, and now that we could do this will be for the later report. Now that we have the step file of the head, and we know what the material is because we know it's now grade 3 titanium, we are now in a position to give a more precise answer. This is from the report I did for the NTSB last year around the September-October timeframe. So we did not have the ability to give a more precise answer. But this, given that it was just an in-house review, let's see what it looks like using the one cycle load, since it was consistent with the potential failure mode, these results are what prompted me to say, I need to send this to NTSB and let the smart guys there take care of this.
Sir, did you run this for like a second cycle, this analysis?
I didn't. And there's several reasons for that. But basically, it was all my previous work was just looking at one cycle. I haven't, if you start looking at multiple cycles, then you have to start asking the question of creep. Now, creep is the issue of a material, any material, steel does this too, under the right conditions, where under a static load, it just kind of moves. It's not quick, but it moves. Acrylic will creep. So if I was going to look at more at multiple cycles, I would have to consider time factors, and that would go in. I'd have to know more about what's going on. And honestly, it's a fairly involved calculation. The setup, and then I had no means to validate it. So I might get a very precise answer and be still way off because I have the wrong material properties, or I have, all of this was done using my default
Comes to grinder, this
military
is
grade acrylic
pretty much
that was done for
as good as
Jerry's
get.
work because I was trying
Yeah,
to
so this is
validate
good
the
as get.
process.
all right. You can
The
do
technique
espresso,
against
you
Jerry's
can
work.
do
I didn't have
filter
the
coffee
ability
really
to
well.
find out
Okay,
who made the
fantastic.
window.
All right. Okay, let's brew some
I
coffee.
didn't know
So
the
I got
details of the window
two
enough at
set
this
up
time.
right here.
This was
Maybe I can
an in-house exercise to see if
here.
there was a
Maybe I
reason
can
to
kick
to
back
act.
a little bit.
And these results led to me
right angle.
sending a report to the NTSB.
Okay.
Yes, sir.
So
I understand.
I
Thank
got
you.
two set up here.
Please proceed.
Today's coffee.
So this
So
concludes
this is a brand new
the
bag from
Windows
Good Brothers
portion of
Coffee
the
from
report.
Tanzania.
So the next
Man,
next
check out
slide
the tasting notes, guys.
is going to the titanium
strawberry
heads and domes.
cheesecake,
A question that came up
ripe
during
cantaloupe,
last week's
and
presentations was what's the
strawberry
difference between grade
cheesecake,
5 and
ripe
grade
cantaloupe.
3?
It's gonna be great. I
Grade 5
cannot wait.
often is listed
So
as
this is the brand new
titanium
bag.
6,
Okay, I'm gonna
aluminum 4
open.
vanadium. That's grade 5. Grade 3 is grade 3. You've reduced your yield strength to 45% of grade 5, and you've basically cut your tensile strength in half. So that's the difference between grade 5 and grade 3. But when we did the analysis using the step file from OceanGate, so we actually had the actual geometry, our initial analysis, now this is a linear analysis, but it indicated there was no real problem here. So once we saw that it behaved in an appropriate manner, that the stress distribution concentrations were consistent with normal practice, and even though there's a small quote unquote hotspot where there's a little bit of high stress, that's not unusual with thick elements, and those will self-relieve. No failure mode was indicated, so we moved on.
And sir, I just want to clarify also that all of the results you're discussing now were done post-incident.
Yes. The results here were done in conjunction with the material provided by the U.S. Coast Guard, in conjunction with our helping out the MBI.
Thank you, sir.
The next topic will be carbon fiber. Now, we don't need to go through the slide in detail. It's just that carbon fiber does make sense. I know a lot of people have an allergic reaction to it. I understand that. However, I also read up about how people also reacted to acrylic. And so carbon fiber does make a sense, and if properly executed, would be revolutionary. There's that minor issue of cost, but take that aside, it has a lot of benefits. And it's being used right now for a number of uncrewed systems, both autonomous and remotely operated, and it has been used with some other crewed systems. So there's this figure is in reference 36. At the end of my presentation, there's an eye chart of 51 different references and stuff. Will not be presented in this hearing, but it is available to say this is where I got my different information from. Since there was no convenient way to put a title block on this is just from reference 36. So bottom line is that the idea of carbon fiber is not bad, but it is, but it does require a lot more work because this is not in the code book. Slide. And this is one of many papers I presented as examples last year at Underwater Intervention it was Underwater Intervention. The point is that other people have been exploring carbon hulls and how to do it. They have looked at doing different spheres. This one shows a more classic submarine hull, but it also has a lot of reinforcement to address the issues of buckling. So Stockton Rush and OceanGate were not the first ones to think of it, and this is an active area of exploration, at least in terms of R&D. However, next slide. Oh, and this is another example where they're using spheres. Next slide. But there are factors to consider, such as delaminations. You don't have that with steel. You do have this with laminated items. And this particular one is specific to a review of structural failure of composite pressure hulls in deep sea. So this is absolutely on point. So this is a known issue, and how to address that is still being worked out. Slide. Other issues include residual stresses in the hull section, which is I demonstrated what residual stresses are in the windows. So residual stresses also occurs in other materials as well, but I was demonstrating that for the acrylic windows. Moisture getting into the carbon fiber is also an issue, and also temperature effects. We have not addressed temperature, but the temperature changes that go from ambient down to freezing temperatures in the water are significant, because moving water is one of the best ways to get temperature changes. The metal changes quickly, but the composite hull and the window are insulators, so they change much slower. So you're more likely to have temperature differentials. All by themselves, not showstoppers, but when you combine it with all the other forces and stresses going on, you can start having issues. Jerry's work, there's a separate paper on this. We examined the work with ASME Designs, and there is an issue with temperature changes, but because Jerry was so conservative, he mapped around it. But if you want to do a new shape, you don't have that option. You can't use it. If you're not using the ASME method, you have to explicitly address temperature issues. Slide. So going into the failure mode with the carbon fiber, we can look at this as, we can assume at this point, for looking at carbon fiber, that the head is good, the window is good, the ring is good, and it's just the load on the carbon fiber. Well, if you look at it in a plane view, as we are here, it's kind of like a bridge. It's just this straight line across a gap, 2 hard points, and it could be either. And normally, when you're doing engineering, you bracket this. You could, and I believe someone talked about this earlier. You can assume it's fixed, which puts more shear stress on the ends, and you can treat it as pinned, which maximizes the bending stress in the middle. This goes back to undergraduate work in engineering. Everyone who has been through strength of materials and beam bending and has nightmares about this. So this is all something that I'm saying the first principles of engineering do apply here. But what I like to do here, carbon fiber is addressed in the boiler code, but only for internal pressure, and they only require for external pressure is a vacuum. So 100 kPa or 15 psig is the maximum that's covered by the code. So there is art in the code about carbon fiber, but it's limited to 1 atmosphere difference. Outside that code, you need VVUQ. But I'd like to illustrate how this would fail in more of an abstract way, kind of a break it down Barney style with cartoon way, just to show the concept of how these fibers can break and how they lead to a failure. So the next slide is a bridge. And this particular bridge is called a Bailey Bridge. And what's significant is it's made of that panel over and over again. It might be 2 and 3 panels thick on the sides. It might be 2 and 3 boxes tall. You change that bridge based on what you need, but it all has the same individual unit strength. The strength of the panel doesn't change. It's how you use it is what changes. Slide. And here's an example. The left is what's called a single-single. It's 1 panel across there's only 1 panel on the side, and it's 1 panel high. It is good for a footbridge or single vehicles, trucks up to 5 tons, depending on the length of the span. It all depends on the design. The exact same system right next to it is showing both a double single where it's a short span, and then it comes to a abutment. It has a longer span across the water, so they go to a double double where it's 2 panels wide on the edges and 2 panels high. It all is about the design. So it's not about the individual strength of the item, as how you put it together. Slide. So what we see here, and this is something that there's no animation on, which is good. The top image shows 20 distributed failures. And part of this design was meant for World War II. The Bailey Bridge, it was designed by the British during World War II. All the Allies copied it. It's been credited for winning the war because it let everyone bridge across gaps quickly. It could take a whole lot of damage. It was designed to take damage. And if you distribute that damage around, as I showed here on the top image, you'd still send an engineer officer out to check it, but let's call it good. But if I put if I break 6 members right there on the abutment on the left or right there in the middle, that will cause a failure because it starts, basically a crack starts and it just keeps walking and causes the whole failure. So when it comes to the carbon fiber, it's not just about the number of breaks, it's about where those breaks are. And what you should do is know how this thing is going to break as you put it under pressure, and then know how many breaks, how many clicks it takes to get to the failure point. That's how the real-time monitoring works. Real-time monitoring is an excellent idea. It is the right approach for composites, but you have to do it correctly. If you don't know how many clicks you need to get to failure, you don't know how many you need to, as a caution, to say, here's where we stop. If you're not counting, if you don't know where the clicks are going to appear, because as you can imagine, if you put the weight in the middle, it'll start having more failures in the middle. It won't be randomized. The thing on top would not happen in real life unless it's being shot at or blown up. In real life, where it's going to be most stressed is where it starts breaking. And you could predict that here's where it's going to keep breaking on a regular basis, but you would test that. You would need testing to know what failure looks like, and then, like Jerry Statue did, back out where your design points are for different actions. So there's nothing wrong with real-time monitoring. There's nothing wrong with saying we're counting the breaks, but you have to know what those breaks mean. If you don't know how many it takes to break, you don't know where it's happening, then all you're doing is listening to noise. The only thing that you would have a value with real-time monitoring at that point would be the rate of breaking. And even that's problematic because the first time you go down to depth, you'll have a lot more breaks. And if you go down to the similar depth or a lesser depth and suddenly start hearing a lot of breaks, you could go, oh crap, that's not supposed to happen now. But all of this is guesswork because basically the model, the design was never calibrated, the RTM was never calibrated to the actual performance of that hull.
So I'd like to just ask a follow-up on this issue. OceanGate's approach that I understand was if the hull became quiet at depth, that would indicate that the vessel or the hull was seasoned to a point that it was safe using the acoustic monitor and the strain monitoring. Can you give an opinion on that approach?
In abstract, it's not wrong. In terms of a macro, let's talk about it. But in terms of implementation, it's problematic. And this, again, I've had a chance to go over a lot of the material that was available. One of the reasons why this was not an accurate statement is that there was a decision not to maintain your acoustic monitoring unless you're doing certain dives. So they would turn it off.
So I'd really, since we're still investigating that,
okay.
I just mean if the hull were quiet or the acoustics diminished at depth, would that indicate in your opinion, that it was?
I would not trust that unless I had done the work to validate that's what's going on. I mean, they're talking about the general principle, but unless you validated your physical model and have basically calibrated your acoustics so you know what's going on with that, I don't know how much I would trust that. Now, if that's in conjunction with being at a lesser, like half of my previous max depth, yes, I would say silence is good, and I would be okay with that. But the thing is that as things go down in depth, similar to what we saw with the acrylic, you're still going to have some flexure. You're still going to have, because it broke to a certain point, when it comes back down, it's going to reset in a different way. You're going to get some more breaks. And the thing is, if it's quiet, but you're at maximum life, how do you know that you're not at the point where the next click is literally the straw that breaks the camel's back? So that's where the uncertainty becomes too great.
Understand. Thank you.
So I just, one slide just to give a nod to the NTSB and all the great work they did. I'm not going to repeat the work that they've done, only to acknowledge that there are 5 layers, that they were cured successively, that there were wrinkles in the layers and voids and gap and a glue laminate between the 1-inch lifts. But we had caught your briefing this morning. That was, I'm not going to repeat that work. They're the subject matter experts for this exercise. So, slide. So I talked about VVUQ. I mentioned it earlier on. What is that? When you're doing cookbook engineering, normal engineering, you open up the International Building Code, the pressure vessel code, tells you what to do. Put in these numbers, get these things out. That's because it's all been worked out. It's been tested. It's been tried. There's for all those different things, there are studies and everything else backing that up. VVUQ is a method that you do for NASA when you're doing something new or high risk, no fail situations. Nuclear reactor, space program. The space program doesn't actually typically, most of our space program has not had crews involved, but sending up a multi-billion-dollar satellite still is a high-risk situation, not just because of the money involved, but the capacity that they are supposed to do. So when you're doing something that's never been done before, the question is, well, what do you do? This is a methodology and that started back around the World War II era, became more serious as we started using simulations and not just slipsticks, where you do simulation and experiments in conjunction to build that body of knowledge. And unlike a code and standard, which builds a broad layer, is using a very broad approach where anyone can open the book and use these rules to do this range of things, this instead is developing the body of knowledge for this one application, for this one thing. Now, over time, you do enough VVUQ, you do enough things, it becomes more and more like a code and standard. You develop that knowledge. But this is how you do something new. This is what NASA uses. This is what the FDA requires because they're medical devices. FDA requires by law, by regulation, I should say, that you use VVUQ if you have software in your medical devices that runs your pacemaker, or you're using simulations because you're trusting this simulation thing to give you good answers. So you have to use VVUQ to make sure those numbers make sense. You don't have, magic numbers coming out of your software. So bottom line on this, it is layers and layers of simulation experiment. You solve that one item, and then you work on your next item. So you have your individual, if you want to think of it this way, you use VVUQ on your individual components to develop your components, and then when you put them into your assembly, now you have to do it all over again because now you have them interacting together. So even if you're using a known commercial off-the-shelf item, you may have to use VVUQ to integrate that in to a brand new thing. Now, I'll get into this a bit, but the concept is very simple. The more unknowns you have, the more VVUQ you need. The less you need, the closer you are to using codes and standards, the less checking you need to do. Next slide. And this is just to illustrate, this is not about any one magical industry. This is not just for specialized things. It is for higher applications, high risk, high money, or highly novel applications that you just can't test by saying, hold my beer and let's see what happens. That has a place for low risk situations where you just, let's see if it works. That sometimes is the best way to see if I can get this new screw to work in this new woodworking thing, but not for something like a manned space, crewed space program. So the point of this slide is just to show, I redacted all the names out, but this is who's on the committee. You have national labs, you have biomedical companies, you have aerospace, power, automotive, defense, consultants. These are the people who are writing these guidelines. Now, these codes and standards are not, these are intended for more advanced engineers. So they're not going to say, step one, do this, step two, do this. These are more guidance documents. But this is, if you're doing R&D work, if you're doing a new manned submersible, this is the right thing to pull up. So when there was assertions that we did it all the right way, and we were doing all, following the rules, not following those, but we were doing it the right way when you don't have rules. This is what right looks like. VVUQ, definitely VVUQ 10, solid, computational solid mechanics. You're using FEA, this is what you should be using. Otherwise, garbage in, garbage out. Slide. This just illustrates that the idea is that in traditional engineering is codes and standards is cookbook. And I termed advanced engineering as somewhere in between cutting edge engineering where you're doing the classic traditional full-blown VVUQ. Well, somewhere in between, you can be doing something that's just outside the code book, but still a known material. We're doing something new. We need to do some extra simulations to check it, but we're not doing something horribly novel that no one's comfortable with. Part of the deal with VVUQ, when you read the manuals, it's meant to inform the project managers, who are often technical people. It's meant to inform you how much risk do you have, how much uncertainty do you have? Is the uncertainty something that we can mitigate? Or is it something that you're just stuck with, that we can't change how much unknowns is here? Because by breaking that out, what is known and what is the known uncertainty and the ones that we can reduce, then you can work that out and start making that part of your plan for your experiments. And how do you reduce that the uncertainty? So when you're doing something like at NASA or the national labs, that's cutting edge engineering. My mentor, AJ McFate, who you saw is on the team, when he was at Sandia decades ago, he was one of the people that was doing the backpack nukes. So they were using this methodology because it was high risk, high cost, just like it fits everything you want to do with VVUQ. But the heads and the controls that we're talking about for the Titan, I would say it's more like advanced stuff. You'd want to do some simulations, you want to test it, but it's not horribly out of, it's just outside the code book, but it's well within established engineering practice. You just need to check it. But the shell, definitely, you would need a whole lot more VVUQ in the window because the basis for the window has so much engineering uncertainty. We just know it works through a lot of empirical testing. But from an engineering point, we're still developing what does the FEA mean and how to predict with that. You would have to do a lot more VVUQ to get that window to be validated. So that's the concept here is as you start doing more in VVUQ, those procedures are actually baked into the code. Even now with pressure vessels, you have to do, you get your MIL certs from the foundry that gives you your steel. Well, they perform certain tests, Sharpie tests and different tests. That's experiment. And they're validating the premise that this is the right material. And they also give you the chemistry to validate that you have the right chemistry. When you fully build it, you hydrotest it. Again, it's a test. So you're actually still doing VVUQ in the cookbook level, but it's much more reduced, and it's more about confirming that this is going to behave properly than we don't know what's going to happen here, but we need to write it down so we can see if we can replicate it. So that's how VVUQ is in a spectrum. Slide, please. I'm not going to beat on this one. I actually talked this piece out a lot about there's the big thing here is that when you're doing traditional VVUQ, it's called non-deterministic. In other words, when you do your normal design, I'm going to do it for this pressure and this temperature and call it good because you're using a cookbook. But when you're doing something like this, you really don't know how going up and down in pressure versus going up and down in temperature interplay. You don't know if temperature is a factor or not. You don't know if the rate of temperature is an issue. You don't know if the rate of the load is an issue. So you check things against ranges. So calling it non-deterministic means you have multiple design factors over a range. It's more money and more time. So the big takeaway here, the traditional VVUQ, which is absolutely needed when you need it, does take time. And that's why it's a national lab thing. It's a NASA thing. It's not fab shop and knocking out your pressure vessel thing. As I said, it's high consequence and extraordinary novelty. We can go to the next slide. This is just to illustrate the idea of there's a version of engineering or deterministic VVUQ, which this is
Sometimes
from some
if
development
I
that
go
we
too long, it's not the same. So okay, here we go. So this is a EK43. The color looks pretty nice as well. Here's the thing about these cups, okay? Because I've been washing in the sink. You know, I smells like. Hold on a second. Hello. Thanks, buddy. Okay, never mind. We got mailman. Just stop there. Stop there. So I mean, I like to rinse my cup first with coffee. Sometimes I rinse with the hot water as well, but yeah.
guidance on load combinations
So
and failure criteria. And the ASB pressure vessel code is one of the most detailed ones in providing all that guidance. So you can actually do a lot more design by analysis with a great deal of reliability. But in U.S. Coast Guard in their shipbuilding has guidance on using FEA. But there are other codes that just give you either some or no guidance compared to the pressure vessel code, where that increases your uncertainty, and you'll have to perhaps do some experiments to validate your design if it seems like it's way out of the standard, but it's still doable. You'd want to check that. So what I'm saying here with respect to the Titan is not everything needs to be treated as if it's Apollo 1. The engineering, the head of engineering, the engineering manager should understand these kind of concepts and be incorporating all this. And all the operational data and all the operational work is engineering, because that's your data. And they have to be working hand in hand. There is no stovepiping. You cannot, every chance you get to operate your equipment, whatever it is, when you're in development or you're using VVUQ, is data. That includes, if anyone's ever run an engine or a generator, you count your engine hours. It doesn't matter, then you count your engine hours. If you're really doing testing, you count your engine hours versus the load. But at a minimum, your engine hours are counted because that's what goes back to the rental place. But when you're actually doing development, you'd be tracking that against your load. And then if you're looking at really getting to development, you'd be tracking your load and your hours versus temperature if you're trying to see whether this equipment works in Arctic versus South Louisiana. So there is a process and there is guidance out there. This does not have to be invented from scratch. And the practitioners are out there that do this. And these are the best practices that are being used in Boeing, Lockheed, General Motors, the same people who are on the Codes and Standards Committee for this, they're there because they use it. So this is not anything new and hidden away. Anyone who's working in this area and reaching out to people should understand this and should be aware of this. Slide. And this is what I was talking about, the pressure vessel code, where there is a solid ring around DBA because they give you all the rules for it. And they even give you the allowable stresses to use. They even, in the pressure vessel code, even give you the methodology to develop your stress strain curve. So they give you that whole system. They give you your materials, your load combinations, what failure looks like. So you can do nonlinear analysis. So you can look at all these different things. Caveat to that, you can't use it for figuring out failures because the design code has built-in factors that if you design to the ragged edge of the line of the design code, it's still safe. If you give an engineer a limit and say, I can design to that limit, they're going to put their toe on that line. So that where that line is in a design code is not going to be one nanosecond away from failure. So, but that was that. And this one is the one about Windows. This is what we're doing right now in development. So you saw about the Windows, you saw the FEA. We're working this system where we're using VVUQ and we're pulling in the different elements of the pressure vessel code and PVH01 into this process. And this is something that we've been working on, for many years, and it was published that we were working on it. So I've been getting emails from people saying, hey, help me out with this, talk to me about this. Other members of the committee have been hit up for people who are trying to do new things, and we've been sharing that information. So when I say that there's a community out there that is working on this and developing it, there's a lot of discussion. And sometimes that discussion is, hey, let me know how that works out and can send me your data. We want to include your data. I'll help you out and give you advice, but give me your data and we'll call it even. So it's not a question of you can't get help without putting money out. There is this whole community that not only is schooled in VVUQ, but they're working actively in the PVHO space to develop this for the Windows. So where we're going with this is why OceanGate needed VVUQ. High risk, well, there's people in it. Also, there's organizational risk, and that's one of the criteria for VVUQ is what is the consequence of failure? The consequence of failure of the, when we lost one of the Apollo missions or we lost the Challenger, that put a lot of things at risk. Is this worth going? It puts a lot of questions into whether the program is going to be allowed to continue. For a company such as
money on it.
OceanGate, where you have this one equipment
so
item
I was hoping
that
this
is
tests for
central to their
something-
business model.
Something
Even
different.
if there was not people involved, the risk to the organization warranted VVUQ. Then you had new materials, novel applications, and novel systems integration. Just because one or two things are known together, do you know how they work together? And really, anyone who's suffered through an engineering education has seen this before. Design, predict, test, measure, analyze, redesign, iterate until it works right. This is not anything that anyone who went through engineering should not, we should all understand that. And the next bullet points were just to minimize the amount of VVUQ, you just minimize your novelty. Documenting things, the more you document it, the more value you have, the less you have to redo it, the less uncertainty you have. Because if you do something and you don't document it, you have not really mitigated the uncertainty because you don't know what it is. You just know it worked or it didn't work, but was it within 50% of failure or on the ragged edge of failure? I don't know, it just didn't fail. That doesn't help. And this is the standard of care. When you're doing something novel that involves risk to the organization or risk to people, this is a standard of care and it's well known within the engineering field. When you, maybe not at the level where you're working in the plants and you're working on, shipboard where you're working with the cookbook stuff, but as you get into the more advanced stuff, it starts slapping you in the face. But when you read the papers and read the books, these topics come up. Do we want to take a break right now? I was about to get into talking about the implosion of the shell.
Are the potential points?
Potential points, yes. I can keep going, but
Red, I think this is a good time for a break. We've been going for a long time, and we are over our time at the facility. So, but I mean, we've been allowed to continue on for a bit. So let's take a brief break. Is 5 minutes enough for you, sir? Okay.
all good.
We'll start back at 5:16.
Gotcha.
There. So what I'm gonna do is I'm gonna bloom for a while. Okay, I think I'm gonna bloom about a minute or so. Yeah, let's do about a minute blooming time. And I want to degas it. Let's see here. Canton asked me, so this is a Kaya scale. Okay. So this is the Kaya scale here. So this is the silver one, and also I have a black one as well. Okay, about a minute. Okay. Now let's go gentle with mellow drip. Right. I know we have the Anton said, don't look at the price of the Archaea lunar scale. I think he's not wrong about that. Okay.
With Peter. So he should be live. Oh, thanks, E2KT. Thank you. There's like a 50% chance I'll go live tomorrow. If I do go live, it'll probably be like in the afternoon. No morning stream.
To make rope, yarns wind around a little at a time. The yarns roll over. This ensures they're at an even tension as a rocking spool called the whirlwind yarn, so it winds evenly.
Like I have a bad
Core
fever and
yarns.
I can't even get out of
The fibers into yarn.
So like, is that 100%?
They place 48 of these bobbins on the maypole machine, so called because the braiding action resembles a dance around a traditional
Bye
maypole.
guys, see you. 50% Thursday, 100%
The bobbins
Friday,
spin
and
and
then
zigzag around each other as the machine pulls core yarn up through the center.
I keep so much
Here you
shit.
can see the rope being braided around the core yarn. As it's pulled off through a die. This is the braiding action in slow motion. It produces a mountain climbing rope. Strong, yet stretchy because of the twist in the core of the rope. The rope winds onto the wheel as it pulls it upwards.
Wire ropes play a very important role in supporting and moving an object or load. In today's Mighty Machines video, let's look at
Years ago, people went to great lengths to make rope. They stretched yarn 200 to 300 meters. They placed
as it pulls it upwards. Then it spills into a basket. A sample rope is pulled.
The machinery has changed. Currently, they're loaded onto these banks and then
to get from one end to the other. The building had to be long enough to make 220-meter lengths of rope, enough for a ship to anchor in 40 fathoms.
And then when the rope makers are ready to close part of the process, 3 of the strands are twisted together to make a finished rope.
This constant twisting process gives the rope its enormous strength. Chatham Dockyard was once at the forefront of shipbuilding. Throughout its history, it provided over 500 ships for the Royal Navy.
And we're gonna enlarge that to 83 MP, exact same design as well. So bring out extremely clean cup coffee. Okay, very clean. So
involving that due to the real-time monitoring system, it's unknown. Warning involving that due to the real-time monitoring system, it's unknown. It's unknown how, since we don't know the exact mode, whether there would be a chance for to hear the real-time monitoring system start making lots of noise, or to hear the carbon fiber starting to break. When carbon fiber starts breaking like that, it causes a lot of noise. There's just one or two bands of it breaking can sound like a sharp explosion or a sharp impact. But if it starts breaking in general, it just makes a lot of noise. The real-time monitoring is supposed to be picking that up well before that point. So if you have a lot of clicking going on that you didn't expect, that would also be an indicator that you're potentially going to failure. But again, it's just unknown. And the last mode involved that I haven't gone into detail was buckling. Now, we can examine buckling in more detail now that we have the material data from the NTSB and we have the more data from OceanGate on the dimensions. Buckling is a rapid collapse of the geometry. It's not something that's readily predicted like a linear failure where a bending mode is you can calculate stresses as it bends. It can be a snap through or oil canning of some sort where it's the mathematic models behind it are a lot more hairy. And you really need to have a solid computational basis for either computer or hand calculations for that structure. So we put that off to the side, and we plan to address that in the report, but we put that off to the side because we were waiting for the material data from the NTSB for that to go all the way through. Are there any questions on this one?
I think at this time, before we get into recommendations that your engineering firm is making, we have a few follow-ups from the presentation.
Sure.
Commander Williams?
Thank you, Mr. Kemper. I'm going to start with some of those failure modes that you just stated because I think it would be a great time to follow up on this. So to confirm, the window failure that you just said that could be a possibility, you have an arrow pointing inward. So is it your opinion or is it your understanding that if that window was to fail, it would go inward and not outward?
Due to the pressure, the only place for it to go would be inwards. The question would be, would it fracture and crack first and give a warning that way, which would be like a cupping where a crack would propagate from the corner and carve out a cup, crack into and cause it to collapse that way, or it could just push through. What's the least likely mode to happen here is to have a leak appear. Just because of the pressure involved, it's going to have such a tight seal of plastic to the titanium that it's unlikely that a leak path will form in a way that it would be a stable crack, especially given the other issues that we've identified with the material.
Speaking of the acrylic, we heard testimony last week that stated that the acrylic window was not included in the analysis of the Titan hull. This is specific to the design analysis for hull number 1. Because the acrylic window would slide, is it your professional opinion, or in your professional opinion, is it appropriate to not include the acrylic window in this analysis?
Absolutely not. It's part of the pressure.
Can I just clarify which testimony could you just repeat?
Mr. Nissen's testimony.
And he testified that it was not included in.
Because of the sliding motion that it would create.
Not included in what?
in the analysis,
When you say analysis, what?
overall system analysis.
Like the test, sorry, can you clarify?
An engineering analysis where they would have looked at the entire system, all of the components together.
So not the testing, but the analysis, engineering analysis of the first hole?
Correct.
Understood, thank you.
That is a very flawed approach. The reason being, at depth, that window is experiencing about 3 million pounds of force. Now, of that 3 million, if you resolve it into axial, let's say that's X, and then, no, let's call that X just for starts. And then going the other way, perpendicular to that is Y, the axial force is about 2.3 million. And the perpendicular force, because of the angled, because you're on an angle, so that force as it comes in is resolving both downwards and into the hull, because it's on that 45-degree angle. That's about 1.8 million. So if you analyze that hull without the window seat acting, even if you just had it as a solid, didn't have it as a sliding element, but just had it as part of the structure, now you have an unbalanced force on the hull. Further, that's 3 million pounds of force that's not included in the analysis. So you've just, that would be, this is literally a rookie mistake that we do with pressure vessels for human occupancy, where someone leaves it out, and I have them draw the free body diagram, walk them through the physics of it, point out, if you leave it out, you've left this out. They go, oh, and we never had that problem again. But it just fails the basic idea of static structure. You would have to, unless you know. The only way I would be okay with this is that this is a known design that's already been tested, and you're just checking against other things. But in this particular case, with the amount of pressure you have, the criticality of it, it's not that hard to do, and it should be. You need to at least have some work where it's none.
Can you explain to me in a simplified term how a strain gauge works?
Strain gauge, okay. If I have 1 inch, if I have this, let's call this 1 inch, and I pull it out to 1.1 inches, that's 10% strain. So when you hear percent strain, that's how much it moved. And the reason why we use strain is because if I say something moved 5 inches or half a micron, what does that mean? But if I say I stretched it 10% or 20% strain, then for that material, it gives me an idea of how much it can do, because like stainless steel, typically you can do 30 to 40% strain, whereas glass is 1 to 2%, depending on the glass. So if I did an analysis that had a fraction of a percent of strain for metal, it would, I'd say, okay, it's elastic. So that's what strain is. That's an important concept. So you put this wire and you embed it in your target. And now when your item's unloaded, that's when you do it. So at ideal temperature, at a 0 point condition, you put your thing in. After that point, and it's going to be a very, very thin thing so that it doesn't add any reinforcement. So you can't just, weld on some rebar and call it good. So it has to be something that has no way to influence the outcome. It's just measuring how much the attached item is stretching. So really what that's doing, it's straining, but because you know how long it is, because it's an instrumented item, you know exactly how far that's straining, and you run an electric current through it. So as the signal changes, it tells you how much strain it is. So because it's embedded in the item, it's telling you what the item's doing. So in this case, if it was the hull, if it was a pressure vessel hull, it's telling you how far it compressed or stretched in the direction the wire is going. often in the strain gauge, you'll have a cross and oriented. So when you take the signals and do math stuff, it'll tell you whether it's going axial or it'll resolve out the vectors. It's vector math. But it's a calibrated instrument that tells you how far the material stretched.
We've previously heard testimony about a loud bang that occurred on dive 80. And we've discussed that there was a shift in strain in both axial and radial directions in specific locations on the hull. Many previous witnesses testified that the reason given for the loud bang is the sub shifted in the frame or the cradle. In your experience with strain gauges, would the submersible shifting in its frame cause a shift in strain?
No.
What could cause a shift in a strain data?
You shift the strain by changing you're either changing the load on the structure so it stretches or compresses, or you change the material in some way. You could do it by heating or cooling it, would also change the strain on it. In the case of something that's under tension, such as fiber reinforced hull that's been cured, and therefore it's tightened up. The fibers are all tightened up. They're not just laying there. Everything's tightened up. That if they suddenly shifted because a laminate broke or something else like that, that release of tension would change for that moment. It would change the how far that wire was stretched. So basically, if you could imagine, if you relaxed, you had a fabric already stretched over a frame, and that was its normal zero state, and then you did something to relax the frame, that would register as a change in the strain gauge, even though it was not about pressure, because there was tension in the item in the first place. But you would have to do something with the structure. The other explanation would be that there was a faulty strain gauge, and that usually would cause like the signal died. If one leg failed, it wouldn't resolve on the other legs. That's part of why you use a rosette, but a cross, because you're able to do signal checking. You also have other strain gauges that also would be giving data, so wouldn't give the exact same data, but it would give complementary data that would either confirm or deny. This particular incident that you've talked about, we've had the data, and we have reviewed it. I've bounced it around the appropriate team members, and we have some thoughts on it.
I think we might wait till the end for that specific question. I do have a question, though, related to this. Could a delamination cause a shift in strain between either interply or specifically between layers?
Yes, could.
If you had been presented with this previous situation, that being a loud bang upon surfacing with a shift in strain in the strain gauge data, as a professional engineer, what would your recommendation have been at the time? More specifically, would you have recommended